Welcome to the video lecture on advanced math models, verifying design needs via analysis. This is Jim Heisey, Senior Lecturer in Mechanical Engineering, Iowa State University. Today we're going to be talking about how advanced analysis allows the design engineer to understand functional priority in the design, reliably set performance targets that are attainable, and verify that critical to quality performance metrics will be met for the design. Key terms that you'll want to be familiar with: performance metrics, engineering specifications, engineering analysis methods. Key to doing advanced modeling is ensuring performance goals are met in your design. Project charters include metrics that often must be met. How do you ensure this? Well, you have two choices. You can design, build, test, adjust, and then test again. The problem with this is the design and test iterations can be costly and often waste time. Or you can do engineering analysis, then build and test to confirm the analysis, which often leads to faster results, allowing you to go directly into production. Good analysis will minimize your testing, as only a few attributes need to be tested on the system to confirm that the math models are correct. If we take a look at the influence of design on the total cost of a product, we see on the left side the actual costs that go into managing a project and bringing the design to production. And on the right side is the influence that each of those factors have on the final cost of the product. And you can see here the design has the smallest cost element, but the largest influence on the final price of a product. So it's very important that we get design right. If we take a look at the demand for toolbox, the three key areas that we're looking at are function trees, functional analysis, and the modeling worksheet that goes along with those. So in review, looking at concept generation, we have been discussing using a structured design approach and breaking this design down into sub-functions so that we can design specifications for those, and then generating ideas to accomplish these sub-functions using things such as morphological matrices and pew charts, then using analysis to help determine the best of these ideas in order to create the best desired design concepts that we can put together, and then evaluate these concepts to choose one design idea to move forward with. From there, we need to look at doing engineering modeling, which is the act of translating our qualitative design criteria into quantitative design problems that we can work with. So we'll start with defining a system block diagram for functional analysis, identify the quantitative inputs and outputs for each component in the box of each subsystem, develop conversion equations for each component box, use free body diagrams to help develop these equations of force, motion, or conversion, then perform engineering analysis of the developed model. From there, select the appropriate components based on the analysis results. We'll find too that we can iterate steps 4 and 5 as needed to refine the abstractive engineering analysis to get us to our desired state of design. Our expectations on engineering modeling is that you can use whatever method you want, whether it be hand calculations, Excel spreadsheets, MATLAB, or analysis software within SolidWorks. Either way, use whatever you're comfortable with, but make sure to double check the most critical aspects of your design. We're expecting you to do modeling on the following items: performance metrics that were listed on your project charter that are deemed critical, any TBDs, that is to be determines, that you might have in your engineering specifications, any safety criteria that is identified as being critical to the product. Then lastly, if you're having to design to any applicable standards, key items in there that must be met in order for the design to be certified. All these ideally should be modeled so that you have a good idea of the chances of success of your product. So our challenge is to define the system. Looking at system definition, we have to understand what are the goals and requirements, and how can we break that system down into subsystems that would help us to redefine the requirements flow down on the design. From there, we can model the system using function block diagrams, looking at function flow, create the equations of force, motion, and or conversion. From there, we can set kinematic constraints and also material specifications to help us lock in what our design must be. Let's look at the example that we've been following up to this point, the NASA robotic regolith mining rover. You can follow along by looking at the example file, the Demandver Excavation Model 2016 Revision 3. Key thing, we're trying to pull together what are the competition requirements through doing analysis and benchmarking such that we can define what we need to do in order to design, build, test, and operate a Moon Mars capable robotic excavation system for collecting regolith that will be competitive at the competition and will meet all the requirements as established by the points table that NASA has published and be as good as or better than the competitors at the competition. We had benchmarked these systems, and we're going to be focused mainly on the Iowa State's Hermes 2 design, and we're looking at optimization to create a Hermes 3 rover. We had talked earlier about the rules and the points that are associated with that for setting our design requirements. We want to do analysis so that we can show that our rover can safely collect the maximum amount of points in each of these categories as needed. Key focus we're going to have right now in this analysis is looking at the mining, the ability of the rover to dig, hold, and dump material with a specific emphasis on the digging part. So our challenge is to take the engineering specifications and get them put into a functional model. We've identified functions and features that are needed to meet these requirements, and we need to establish some measurable values or metrics in order to verify the performance of our system. Often NASA refers to this as doing a requirement flow down. So we have to identify what functions and feature values are needed in order for the system to meet the requirements, or in this case be competitive, and what are the goals that are quantifiable, or does the design have any attributes that exist that have to be tracked. From here we ask ourselves, are there some functions and features that can be combined in the system in order to simplify it? Can some of the function features be combined to simplify the system? Starting the analysis, then we want to establish for ourselves some boundary conditions that we need to work with before we can get the analysis going. Some questions to ask ourselves regarding the NASA competition. How much do we have to collect? How fast do we have to go? From there, that would lead to how far do we have to go, how deep and how wide, which will then lead us down into how much power is required to do this. From there, that will help us then to define what components have to be put together in a system to meet all these needs. Along the way, if we make any assumptions, we'll need to make sure to record those. So the first part in doing a good analysis is to just do a quick systems function list. That is, look at the requirements of the system. How does that create for the system functional requirements in order to create for the system the actions needed? And then can we break that down into a function tree diagram so we can see these systems and these functional requirements? We can start by creating what's called a function tree and the function flow diagram. I want to note too that sometimes a function flow can also go across subsystems as well as through a particular subsystem, so we want to keep track of that as we model our system. If we take a look at what we would put together for this rover, we can see the function tree here on the upper right hand, and we'll notice we have highlighted the collection system. That's what we're wanting to deal with today. And then we've laid that collection system out, looking at each of the components or subsystems in there, laying that out and tracking all of the flow of energy or signal or mass through the system by listing the units here. We also can take note at, as we're doing this, going back to the custom requirements and establishing what our target values are. We're going to see that a number of items here don't have a value yet, but we know they're essential. So these are items that we're going to need to model in order to understand our design fully. If we take a look at the engineering specifications, we'll often see these unknown values creep into the engineering specifications as well, thereby further driving home the need for analysis. So again, if we take a look at our NASA excavation rover and its function tree, we're going to focus on the collection system, and we're going to put together a block flow diagram such as we shown here earlier, noting the flow of all the signals through the system. Our main concern here, we're going to look at the upper part of it, dealing with the collection motor and the scoop system. So we simplify our system for the sake of building a model. We want to take a note that each block has an input, it has an output, and then there's control parameters that go with it. If we track the inputs and outputs through the units that are going to be going through there, these quantifiable items that we can measure, it helps us better establish our model. Along with that, if we take a look at what parameters go within each element here that affects its operation, that will help us to then establish the control equations that would be generated in order to model the system. Alternative layout on building a function flow diagram, we can lay it out vertically as shown here. That gives us the advantage of laying the equations of motion alongside the particular text box that describe what is going in that particular function, and we don't have to grow that flow chart larger than necessary. If you'd like, take a minute to pause the video here and look through each of these equations and understand what's being pulled together here for the system model. Now, in starting our analysis, it's going to be really important to organize your notes, record critical decisions that you made, and then get those into your documentation. Oftentimes, I like to take and make hand notes on things and then scan that and insert that into my Demandver toolbox. It gives me the opportunity to record any of the knowns that I have, any of the assumptions that are made, and then also to help establish the equations of force and motion that I have to model the system. Also, I can put any other graphics in there to help me to further define what's going on there. Key thing when putting in documentation in the Demandver toolbox, when scanning a document, save it as a PNG or a PDF or a JPEG drawing, not a bitmap, and then use the paste special picture enhanced metafile command in order to insert those scan pages into your Excel toolbox. The main reason for doing this is that if you just simply copy and paste, it's going to paste it in as a bitmap, and then the file size of your Excel file will become huge and it'll be ungainly to open, and it will be too large to email to others. So again, if we take a look at the requirements flow down, in this case we're going to start with taking a look at what defines a sortie. How fast do we have to move, how far? So we take the map that we have of the arena and we track what are the distances that a rover has to go, and how can we break those up into time function elements. In this case, as we can see, distances to travel, we have to go out from the target area and the bin through an obstacle area, which is going to take us a travel length of about 3.9 meters. Once we get to the edge of the mining area, we can stop, create a starting point for our rover, and then mine out 2 meters, and then back up, stop at that point, scan for home, and then return back through the obstacle area, getting lined up with our home site, which then we can unload and then repeat the whole process. The whole travel distance through that process is going to be a little over 11.8 meters in distance. So from there, then we can find our travel velocities. So we take a look at the total amount of time we have available to us. We can break that up into time elements, which we can see here for the set time quotas for each event. That is, we're going to track how much time it takes us to go out, mine, come back, and then zero up to home and return, unload, and then repeat. You'll notice too that we have some events in here that we can pull out early, which is the time required for localizing the rover in the work area. And then we have pause times between each particular step in the sortie, where the computer makes a command decision and then the rover responds to that command decision. Time pauses in watching the videos typically to be at 5 seconds, so we'll take that as an average and continue forward with analysis. If we take a look at the travel velocities as well, then we can find that the time, distance, and speed quotas required for the amount of regolith that we wish to collect. In this case, we want to get a minimum of 200, a max of 300, and our hopper has a capacity of 50 kilograms. Some simple math will tell us that that means we're going to be wanting to run at least 4 and probably no more than 6 sorties in a mission in order to get the desired amount of regolith collected. Also, again, pause time being 5 seconds and localization time being 30 seconds. We can pull that time out And in the end, with 6 sorties, we'll find that in our best case scenario, we got to utilize 70 seconds in each run in order to get our required 5 sorties in the 600-second allotted mission time. Here again too, we've made some assumptions to go along with this about hopper capacity, time delay, localization time, and the distance traveled in each sortie being consistent. So looking through the analysis, again we're recording some other assumptions we made. The mining speed will be 1/3 of the transport speed in order to accommodate most models motor controllers that could be used on the rover. Key thing is speed accuracy gets lost below 10% of the max velocity, and that the transport velocity is going to be 3 times whatever the max mining velocity is. With that, we can establish our equations of use, and we also have some knowns that can contribute to the success of our model. So here we take a look at breaking it up in time. We have the time for a sortie is going to be 70 seconds, and that's going to be made up of going through these various distances and their resultant velocities. Since transport velocity is going to be 3 times mining velocity, then we can solve for everything in terms of the mining velocity. And in solving for these equations, we're going to find that the desired mining velocity site is, if we take a look at the time calculations here, we'll see that the desired velocity for mining is going to be 0.105 meters per second. And as a result, with the transport speed being 3 times faster than the mining speed, then the transport speed is going to be 0.316 meters per second. Another thing we need to determine in setting our mining, if we want to collect 50 kilograms in this 2-meter run, then we have to figure out, given our dig width, how deep do we have to dig. If we take a look at the average regolith density being 1.5 meters per second, then that determines for us that our dig depth, in order for the 2-meter run in the mining area, is going to have to be digging at 9.4 centimeters down. Once this is established, then we can calculate our mass flow rates in collecting regolith. The next goal we're going to do is find the conveyor speed. So we look at scoop volume and scoop spacing, and we have a forward travel speed established of 0.105 meters per second. Then we can look at this from a mass flow rate standpoint, because we know that as the rover is moving forward with its mining speed, it's digging a trench that has a fixed width and a fixed depth, and that these also need to be equivalent to the mass flow rate that's established by the scoops running, which is the velocity that the scoops are running to, capacity or volume of each scoop, and the pitch distance between each scoop. These have to match up in order for a balanced system. So we work through this and solve for the velocity of the conveyor, then we'll find that that number comes out to be 0.745 meters per second. However, if we adjust the mining depth slightly, we'll find that we have to pick up the conveyor speed in order to make up for the increase in volume, in which case now the conveyor speed goes up to 0.793 meters per second. Not enough, but in most circles enough to keep track of. After finding our digging velocities and our belt speed, we need to figure out what is the force required to dig. With a little analysis and research, we found a universal digging equation that helped us to establish what the forces of scooping is around the blade tip, as we can see in figure B in the middle of the sheet here, which lays out the parameters. We also notice that because the rover is moving forward while digging, that creates a progression distance, which in this case we define as XP, and that's going to be just slightly under 1 centimeter for each scoop coming through at the speed it's going to be running. We'll also notice that the area that's being scooped out based on the depth and the width that we're digging out is going to be 0.0019 meters squared. With this information, we have enough information we can move forward with establishing our digging forces. So one of the key factors, again, we're wanting to understand scoop forces. We used a fundamental excavation equation and applied that understanding to our math model here. Came up with a final equation to describe force as a function of density of the material, coefficient of friction, the progression length, and then the angle of sweep that the scoops are going through, and then comparing that as well to the binding width that we have. So we take this equation and put that into Excel, and then we can come up with our force equations based on the rotation of the mining conveyor. These are results from the model that we put into Excel, looking at the scoop forces for a single scoop, and then what the progressive scoop force is, and a continuous running belt from the initiation of digging. And then we also lastly looked at the conveyor belt load and the mass collected for a half cycle on digging conveyor. And as you can see, we're going to have a peak force load of about 360 newtons, and it's going to oscillate between that and 259 newtons based on the speed of the conveyor, the depth that we're digging, the speed at which the rover is moving forward as well. We can calculate the torque requirements based on the force in the belt and the radius of the conveyor drive, along with the force on the scoops and the radius out to the tips of the scoops. Again, we have the torque requirements as we established being 24.9 newton meters, and the rotational speed of the conveyor being at 15.61 radians per second at the drive wheel. If we take a look at the power requirement of 389 watts for mining, and if we understand that the drivetrain is only 80% efficient, then we can calculate the power required at the output shaft of the motor, which in this case winds up being 486 watts. If we take a look at motor performance curve, in this case we're interested in using two VEX Pro bag motors. The two motors combined, if we apply enough voltage, turns out we can get enough power capacity out of them. The motors rated 486 watts apiece. So if we take two of them and run those, then we find that the load requirement on the motor is going to be somewhere around 0.177 newton meters in torque, and that the motor is going to be running at about 243 watts output power, which will be adequate to cover our needs. And as you can see by the chart here, we still have a little extra power reserve left in the motor in this condition. If we look here at the motor performance versus load requirement, we can see the blue line represents the motor torque speed curve. Brown dots represent the power requirements, both with torque and speed, for the conveyor system to operate at these given reduction ratios in the drivetrain. And as you can see, the one we've selected is the 90:1. Lastly, we got to do drive ratio selection. For our two bag motors, we're going to be running a dual drive and through a versoplanetary gearbox, but we have to determine what ratio. In this case, doing the analysis, showing the data in the table here, the team chose to go with a 100:1 gearbox. We can see with the table on the lower left giving us various different ratios, and enhanced motor speed requirements and the torque required, and we're able to track the efficiency of the system for these various gearboxes. The motor performance load requirement chart on the right gives us the balance between the motor performance at 16 volts and then what the various gearboxes require for RPM and torque out of the motor in order to be operable. We'll notice here too that the crossover point looks to be a 90:1 ratio, though for 2015 the team chose a 100:1 ratio to have a little extra power reserve, and it worked out reasonably well. In looking at advanced math modeling, we want to use the formulas and results to help us with the design failure mode effects analysis and building our risk management plan. We want to continue the analysis through to the final design to identify any efficiencies and establish design factors for stress and reliability. And then also, we're going to save ourselves time when we sit down to do the CAD modeling of our final system, because we can match the math model parameters to the CAD physical parameters and set those quickly and have good confidence that our design will be correct. This concludes the lecture on advanced math modeling. Thank you for taking time to watch this lecture.